Hello everyone, thank you for being here today. My name is Maddie Owens and I am a senior at the University of Alabama, Roll Tide, and we are researching low-cost accelerator and strength enhancer for cement mortar produced by the carbonation of lime slurry. So to start out, we need to look at the industry as a whole. Concrete is the most used material in the construction industry. It accounts for nearly $440 billion spent every single year. However, it has two main problems. It has a carbon problem and it has a waste problem. Every pound of cement produced produces nearly a whole pound of carbon dioxide. This is responsible for nearly 8% of all total emissions by humans global. The second problem is a waste problem. Nearly 6% of all concrete created goes straight to waste, along with almost 200 pounds per cubic yard of washing water. This results in nearly $4 billion of missed opportunities for the industry. We can combat this CO2 problem by using the concrete itself as a CO2 sink. When the CO2 comes in contact with a calcium-rich material, it precipitates as calcium carbonate. This calcium-rich material we can use as cement clinker or hydration products, and when this calcium carbonate is incorporated into our concrete mix, it works as a permanent storage of carbon dioxide in the mix. Now, there's a couple different ways that the industry utilizes this CO2 sink. The first way is through carbonation curing, where the curing water or steam is replaced with purified CO2 and is used to cure the concrete once it's been molded. This gives improved strength at early age stages for the concrete. However, it has limited applicability. It's used mostly for small, non-reinforced concrete blocks, and it can only be used for precast concrete, not ready-mix concrete. And when using the precast concrete, it requires a chamber for the CO2 injection. The second way that the industry utilizes CO2 injection is during the mixing process. While the cement and aggregates and water are being mixed, it is injected with purified CO2. This is able to be used for both precast and ready-mix concrete, and we do see a moderate strength improvement with this. We see about 5 to 8% of the cement is saved during the process. However, it does release some carbon dioxide back into the air, and only about 0.2% of the weight of the concrete is utilized as a CO2 storage. So we decided to create a brand new way in order to keep more of this CO2 in the concrete mix, and we call it the BioCarb method. During this method, we take our calcium-rich material, which is either cement or we like to use things like lime, and we take our biomolecule, which is usually tannic acid, and we mix it with our mixing water. We then use that slurry and carbonate it, and then mix that carbonated slurry in with the rest of the cement and any other aggregates. Compared to the other two ways that use curing and mixing, we actually carbonate before the mixing process. During this method, there's a few different things that go on behind the scenes. During the mixing process, we form nanoparticles of calcium carbonate. These calcium carbonate nanoparticles allow the calcium particles to spread apart, and this allows more of the carbon dioxide particles to come in and attach themselves to the calcium material, and that way more of the material works as a CO2 sink. The biomolecule that we use also has several different functions during the process. It regulates crystal nucleation, orientation, size, and phase. It disperses these nanoparticles throughout the mix, which also allows more CO2 particles to it allows us to keep more carbon dioxide particles in the mix. It refines our final microstructures of these particles, and it could possibly form other composites. Now, looking at the CO2 uptake after just 60 minutes of carbonation, we can see that the CO2 uptake goes up to about 7.5% weight of the cement. Compare that to the 0.2% weight of cement that I mentioned earlier, and you get something that is nearly 30 times better than any existing technology. And keep in mind, this is only for about 30 to 60 minutes of carbonation, depending on which biomolecule you use and how much of that biomolecule you use. But none of this matters if the cement or the concrete just falls apart as soon as you finish curing it. So we need to look at the compressive strength over time. You can see on this graph, we measured the compressive strength at 3, 7, and 28 days. We compared it to our regular control batch in orange, which is not carbonated and does not use tannic acid. And we compared this to carbonation with and without tannic acid. You can see in purple, the carbonation with tannic acid is nearly 25%, has nearly a 25% strength improvement at 28 days compared to the control. And we have over a 20% reduction on our carbon intensity using the carbonation and tannic acid. Now, I did mention before that we use a couple different calcium-rich materials. This graph just shows using regular cement, but we also like to use slaked lime in our processes. We use this for a couple different reasons. It's less energy intensive than cement, it's a low-cost accelerator, and it's ideal for the quick turnover rates that the precast industry needs. It's more expensive than cement at the time, but only because of the relative production rates of both materials. We take about 5%, we take 5% of the cement and replace it with lime, and then we use all of that lime in our slurry and carbonate it. So, looking a bit more specifically, we have our recipe for our concrete mixes. The number before the capital T shows how much tannic acid we used, the number before the capital L shows how much lime we used, and the number before the MC shows how long we carbonated it for. So we look at anywhere from 0 to 0.3% tannic acid, and then we use the same amount of lime for all of these mixes that you'll see. And then for the carbonation, we look at 0, 40, and 60 minutes. So, looking at the compressive strength over time, once again, you can see the shaded bars represent mixes with tannic acid, while the non-shaded bars represent mixes without tannic acid. We look at, going from left to right, 0 minutes, 40 minutes, and 60 minutes, depending on the color of the bar. And you can see, looking at the 3-day mark with carbonated tannic acid mixes, the strength is nearly as much as the control strength at 28 days. Looking at the 7-day mark, these carbonated tannic acid mixes are almost as high or higher in compressive strength than our control batch at 28 days. And looking at the 28 days, we don't see a plateau or a decrease in strength. It actually continues to increase as time goes on. So we see nearly a 25% improvement in strength at 28 days with no, plateau or decrease in strength. So, looking at the industry as a whole, once again, there's several different benefits for our process on the industry, the main one being environmental benefits, of course. Looking at just the US every year, we could potentially permanently store almost 6 megatons of CO2 every year in the concrete that we create. We can save nearly 20 megatons of cement every single year, and we can reduce carbon dioxide emissions by nearly 24 megatons every single year. Worldwide, this accounts for nearly 2.3 gigatons of CO2 emission reduced every single year. So, to wrap everything up, our BioCarb method is nearly 30 times more powerful than state-of-the-art technology. We see early age improvement that's maintained at the later stages. We can use slaked lime as a viable alternative because it's less energy intensive and allows a lower cost with its nanotechnology accelerators. And our BioCarb method can be used by the industry with its quick turnover rates.